Hey there, everyone, it's Alejandro, and welcome back for day 205 of me doing the Daily LeetCode Challenge after I reach 1 year's worth of great contributions here on GitHub. So today's problem is for February 6, 2025. And without further ado, let's get straight into it. Okay, today we get LeetCode Medium, problem 1726, tuple with same product. Given an array nums of distinct positive integers, return the number of tuples a, b, c, d such that a times b is equal to c times d. Oh, we've had a problem similar to this in the past, where a, b, c, and d are different elements of nums, and a doesn't equal b, c, oh, doesn't equal c, doesn't equal d. Okay. Oh my gosh, just for something like this, there's, oh my gosh, okay. And what's the constraints? 1,000, so you can write an n squared solution. This is interesting. How do you approach something like this, right? I remember there was something smart where it's like, oh gosh, I forgot which problem that we saw that was similar to this. It might have even been in a LeetCode contest, but I remember there was something smart that you could do. Where like what I did was like, I took like the products of every single number, then started comparing. Okay, I started comparing pairs, right? If we're talking pairs, something like n squared is fine. Oh, all elements and nums are distinct. Okay, well, okay, first of all, that makes things very easy. All right, so essentially, set res is equal to a set for num and nums. Yeah, so yeah, for I and yeah. So we can't do n to the fourth, obviously, right? Now we can take every single product. We can compute every single pair of products, right? And remember their indices. Oh yeah, if we compute the result in terms of indices, then we're chilling, right? We're chilling. So I think that's what I would do, right? Get every single product in the array. Maybe map products to indices that work for that product. Yeah, so here what I would do is like, okay, we'll do n is equal to length of nums. Here we'll say d is equal to this. And maybe we should make this a default dict of a set. Yeah. It should be really list, right? It'll be unique indices at the end of the day. Here we'll say, or yeah, so here what we need is lambda this, but we can really just put in the function list because it defaults to an empty list. Okay. Here what we'll say is for I in range n, for j in range I plus 1 comma n. Yeah, so here with the constraints, we're allowed to go crazy with an n squared solution. We can't go cubic, we can't go to the fourth, right? Because the trivial way of doing this would be like, return a comma b comma c comma d for num I, j, k, l. Yeah. A in nums, for b in nums, for c in nums, for d in nums, if a doesn't equal b doesn't equal c doesn't equal d, and a times b equals c times d. Right? So like this should work in theory. Numd for nums. No? Yeah. Here we'll just do sum of this. No? set. And we'll just do length of the set, right? Why am I getting 20? What happens if I return the actual set? Three, four, 3, 4. Okay. For I in range n, right? I1 for I2 in range I1 plus 1 comma n. IJ for k in range j plus 1 comma n. For L in range k plus 1 comma n. Do A, B, C, D equals nums of I, nums of j, nums of k, nums of L. If A doesn't equal B, doesn't equal C, doesn't equal D, and A times B equals C times D, then we'll say res equals 0, res plus or equal to 1, and then just return res, right? But this is like, you know, this is what I mean. This is an n to the 4 solution, which is just, how's this wrong? What? Oh. Interesting. Wait. Okay, if we're not, okay, we're not even getting the brute force solution here, right? I just wanted to show this for demonstration purposes. But wait, maybe I'm actually finding something interesting here. 2, 3, 4, and 6. Maybe I want to try all possible permutations, right? Maybe I should make it the min and the max. Right? Sorted. And I want A and B to be like this. But now I'm only going to get one permutation. No. Maybe we just do plus or equal to 8. Yeah, there's just going to be batches of 8 for every single time we find a result, because you can essentially put them in any order you want, right? Because it'll always be 4 fixed integers. Right, makes sense. Okay, that's a cool little realization. Okay, but yeah, obviously something like this is going to be way too slow. Way too slow. We have n to the 4 solution, right? Da-da-da-da-dum. Ba-da-be-da-boom. Ba-da-ba-da-bing. Yeah, so TLE, very nice. Okay. So we have a brute force of n to the 4 solution, right? We might as well put n is equal to the length of nums up in there as part of the solution, right? There we go. Now let's just do something better. We'll say d of num1 is equal to nums of I num in enumerate nums product equals num times nums of j. Here we'll say product dot appends extends as well as j comma I. Print f string d equals. Or really, maybe I just need one. That appends I comma j. Right, that way I can essentially guarantee uniqueness, right? Because I can just have a factor of 8 for everything. So 6 only has one thing, we don't care. Ah, now we have pairs, right? Essentially, the number of pairs we can make, there will be a total of 8. Right, so it should really be based off, so it'll be the number of pairs you can formulate, right? What's the number of pairs you can formulate? Is it n times n minus 1 over 2? So 2 times 1 over, is it that? Right? I just remember that because I looked up, I was looking up birthday paradox a few weeks ago at work, and in order to count, number of, so it's like, it's like, 1 plus 2 plus 3. So it's like, for the very first one, it's like, if there's n elements, the first one has n minus 1 things to compare with, the second one has n minus 2 things you compare with, right? Until the very one, it has nothing that I compare with, right? So you essentially have 1 plus 2 plus 3 plus dot 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 plus n minus 1, which is equal to 1 plus 2 plus 3 plus dot 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 plus n minus n, right? And this is a known summation, which is equal to n times n plus 1 over 2. This is all minus n. So this is equal to n squared plus n over 2 minus 2n over 2, which is equal to n squared plus n minus 2n over 2, which is equal to n squared plus a minus n over 2, which is indeed equal to n times n minus 1 over 2. For each array indict of length n, there will be such many pairs. Right, let's make sure. Now for every valid pair, we can construct 8 valid tuple permutations. So for each product, we will consider the total number of tuples as number of pairs multiplied by 8. We simply take the sum of this value for each product in D as our result. I would hope that something like this works, right? So let's just do something. Return sum of, we'll do for key and D, for here we'll say for val and d dot values num pairs is equal to count is equal to length of val for key and D. d of key count times count minus 1, which is guaranteed to be even, right? Because we're multiplying, since we're doing a number and a number minus 1, one of them will be odd, one of them will be even, so divided by 2 is totally fine. Res plus or equal to num pairs times 8. Return res, right? Does something like this work? Okay, so it gets accepted here. Let's see if it works when we submit. A little slow. And there we go. Completion streak 205 days. Consistency is key. See ya tomorrow. Okay, although we're a little bit slow. Can we do this better in any single way? Maybe we don't even have to append, right? Can we instead do something like this? Yes, we can. Okay, that brings us way down. Okay. Here we can also probably just do times 8 only once. And maybe that's also a bit faster. That kind of... yeah. Especially here we want every single pair. There's no way to go around that. And d.values. Yeah, okay, we'll just do a whole division. Although this might be faster, right? What if I did something like this? Hey, we're getting into the big leagues now. Okay. We're making things fast, ladies and gentlemen. We're making things fast. Alright. If I do this, do I get into loss of information? Maybe not. Which would mean no need for an int at O. Okay. Yeah, otherwise I can't really figure out how to do this, right? Because here you're dealing with products. There's at most n squared products, but you don't know what the values are, so you definitely should use a hash map. Here we could just do... maybe it will be faster if we do this. We'll just do this. D of product, d.get product, comma 0 plus 1. Does this make things faster? Oh my goodness, it makes them way faster. All right, there we go. Okay. Slowly but surely making the solution better. Okay, I'll just keep the brute force solution just for explanation purposes later on. Okay. Nice. Here you can just do res plus or equal. Variables are cheap, and it makes the code cleaner. Okay, there we go. So, bada bing, bada boom, there we go. We have a nice and efficient solution. So, as always, in all my videos, I do a quick recap if I was able to solve the problems. For this one, we took it one step at a time and so on. Finally, we got a LeetCode medium after a crazy streak of easies, which I don't know what LeetCode is cooking up for us, but it smells like 10 LeetCode hards in a row. So maybe they're preparing us with a nice little medium in the meantime, right? They're like playing disguised wolf here. Anyhow, the way that I was able to solve the problem is that obviously the very first naive solution is essentially you want to know the number of tuples such that it is the case that A times B is equal to C times D, and A, B, C, and D are numbers and nums, and it's not the case that any of them are equal, right? This kind of is a red herring that threw me off, because here they just tell us that every single element in the num is distinct, so this is always going to be true no matter what, right? Basically, it means you can't reuse a number itself, right? You must, find products with other numbers in there, right? And so the very obvious way to do things is essentially to do a quadruple for loop, right? I was essentially trying to do this to show that, solving the problem is quite easy, but I actually made a realization when I did this, right? Here, essentially, whenever you find a valid case, right? If you're going to multiply, if you want to find a case where A times B is equal to C times D, you're going to try to go through every single possible, indices and nums, right? So it's like, for I in range n, and for j in range from I plus 1 to n, and then for k in range from j plus 1 to n, and then for L in range from k plus 1 to n, right? Grab those 4 unique indices, grab the number values of those, and set that to A, B, C, and D. Now, if I want it to be the case that A times B is equal to C times D, since here we know that all the numbers are positive, we might as well know that, like, okay, the only case that's ever going to happen is if A and B are, like, let's say the minimum max values between A, B, C, and D, and C times D are, like, the middle values, right? So essentially, if you sort them, right, you want, like, C and D to either be the 2 middle values or, like, the min and the max, or A and B to essentially be, like, the min and the max or the 2 middle values, right? It's kind of like, when you play foosball with your family, if you have a family of 4, it's like, youngest kid usually goes with, like, the father, because, like, the father's, like, the best foosball player, and then the little younger brother is the bad one, so, like, big brother and the mom, play together, and there you go, you have a nice game of foosball, right? You have the worst player and the best player play the 2 middle players, right? Kind of the same thing here, where you want the multiplications to be the same. Since every single number is positive, you might as well have the smallest and the largest compared with the 2 middle values, right? So that's why I sort them and say, okay, let's make A and B my, smallest and largest, and D and C be the 2 in the middle, right? And so then as long as this is the case, which is actually guaranteed to be the case, so I could remove it really, just because of the problem constraints. But otherwise, what I really want to check is as long as it is that A times B is equal to C times D, then I'm going to augment res. But now here you're going to see I augment res by 8, because actually doing it by 1 is incorrect. The reason is that if you find, like, a combination of numbers that work, essentially there are 8 possible permutations that you can essentially combine them as to essentially make it work. And it's simple math, so essentially it's like oh gosh, it's 4 choose 2, which is 4 factorial. So the amount will be 4 choose 2, which is equal to 4 factorial divided by, it'll be 2 factorial times 4 minus 2 factorial. This is just 2 factorial. Am I even doing this right? This will be, no, I'm not doing this right. Is it it's permutations, right? Even then. Why is it 8 tuples? 2626, 6262. Yeah, so you can put it here, put it here. Or you can put it there, right? So essentially you can have 2 6 with 3 4 or 4 3. Then you can have the 2 6 reversed with, again, 3 4 or 4 3. Or you can have everything in the other order, right? 3 4 2 6, right? But the point is, or is it 4 factorial choose? It can't be choose 4. It's essentially how many permutations can you do it where? Is it not 2 choose? It's like you can, no. These can be the difference. So it's a bit more complicated than that, right? But the point is that, okay, I'd have to think about what the actual, I always sucked at the combinatorics part of discrete mathematics, right? So I'm not even going to pretend that I'm good at that stuff. But the point is that here there's always 8 valid tuples whenever you find 2 permutations that are the same, right? The reason I notice that is because, like, in the test case, it's like, okay, this is suspiciously 8, but really, like, there's only 4 numbers you can pick from, right? And here's, like, there's 16 valid tuples and so on. So it's like, okay, 2 times 8, I'm guessing there's only, like, 2 possible solutions. Something sus, right? And so I tried doing plus 8, and it did end up working. So really what this means is that every single time, you find a valid A, B, C, and D, essentially there's, like, 8 ways they can arrange the A, B, C, and D to make it valid tuples, right? You could do, A, B, C, and D, as well as, A, B, D, and C, right? So that's one where you have A and B at the beginning. Then you can flip the A and B's, and again, keep the same C and D's. You can hear B and A, and D and C, and then you can just do the whole thing in reverse, right? So now we'll have the C and D first, and now the A and B, or you can have like, you know, the C and D, and then the B and A, and then finally you can reverse the D and C, right? A and B, and then here it's like D comma C comma, this should be B comma A, right? So essentially, if you have a valid A, B, C, and D, there are 8 possible tuples that are valid that you can make with those A, B, C, and D values that will work for this problem, right? And for this problem, you only care about the count. So whatever your res value variable is, you'll just add 8 to it, right? Whenever you find a solution, there's 8 possible tuples you can make out of it. So you just add 8. So just, you know, weird little caveat of the problem, but okay, sure, we'll do it, right? But the point is that, like, you know, there's always 8. Whenever you find an A, B, C, and D, there are 8 possible valid tuples you can create using that valid A, B, C, and D, right? So that's kind of the point. Now, getting rid of this brute force solution, I essentially found a better way of doing going about things. The better way is essentially, it's like, okay, if I just want to compare products, right, I might as well just pre-compute every single product that I can get out of nums, right? And the way I did that is like, okay, let's literally do an n squared loop and get, you know, the product of every single number in nums, right? So for every single, you know, here's like, you know, for, I really should call this like, you know, for I in range n, and this will be nums of I times the nums of j, right? So here's like, you know, for I in range n, for j in range, after I up to n, let's get the product as nums of I times nums of j, right? And then that will be our product. Now we want to get all the possible products, right? But better than that, we want to essentially count. So before, what I did is like, you know, I had pair of indices instead of a list and so on and essentially because I kept going through about the problem. But really the only thing you actually need to know is the frequency that a product gets mapped to, right? So how many unique pairs of indices essentially map to a specific product, right? For example, if I took index 0 and 1 here, it would be values 2 and 3. 2 times 3 is equal to 6. So the indices 0 and 1 as a pair map to a product of 6, right? So out of every single product you can get inside of nums, essentially, you want to ask yourself how many unique ways can I essentially get to this product, right? Where the unique ways are essentially unique pairs, right? Unique pairs of indices, I and j inside of nums, right? So that's why for I in range n, for j in range I plus 1, whatever the product is, I will augment the frequency of that product by 1, right? I'll get its value, otherwise 0 by default, and add 1 to it, right? That is essentially the point. Here is just for, like, you know, performance reasons, I do I comma num and enumerate num, so that way I don't have to index at I every single time. It's just, yeah. But this is just O of 1 optimizations. It doesn't really matter with anything, right? But the point is that I essentially have a dictionary which will, like, you know, essentially we loop through every single pair of numbers in nums, right? And for each one, we compute its product. And we store the frequency of each product we ever found inside of a dictionary, right? And now once we have that, essentially, we can say, okay, for each frequency n, edit, D is now updated to reflect indices for perf reasons. The same idea applies. There we go. Okay, so before essentially I had it, I used to have, you know, the dictionary essentially be a list of those, you know, unique pairs. So now that you have unique pairs for a certain product, what you want to ask yourself is like, okay, for a certain product, let's think about, like, you know, if I have, like, you know, 2 unique pairs and so on. Like, okay, for example here, let's just do d of product dot append I comma j, right? And let's bring this back to a default dict of list, right? And here we'll say print f string d equals, and then return negative 1, right? So this will be an invalid solution. Right, so now we'll get a wrong answer, but let's print something like this. This means that the product 6, right, the indices 0 and 1 map to 6. Makes sense. 0 and 1 here, 2 times 3 is equal to 6. 8 is mapped by 0 and 2. Okay, 0 in index 2 is 2 and 4. 2 times 4 is 8. That's very true, right? Now let's look at something like 12. Now it has 2 indices that map to it, right? And we know that that's going to be the only valid solution, right? And essentially this is going to be like, you know, the indices which are A and B are located at, and the indices which are C and D are located at, right? And these pairs of indices form a valid pair with each other such that, you know, A times B is equal to C times D, right? Because this pair of indices and this unique pair of indices essentially map to 12, right? Which is very nice and convenient. And so what I figured is like, okay, for each product, we can essentially count, you know, the number of unique pairs that are in there, right? And map them all together, right? So, because again, the whole point is to have every single potentially valid tuple, right? So whenever I find like, a product that's mapped to every single, pair of tuples, even if it reused, right? In this case, it's like, 0 and 3, 1 and 2, they're all different numbers, but it could be 0 and 3 and 0 and, well, actually all the numbers are guaranteed to be distinct, right? So 0 and 4 wouldn't really work. Because of all the numbers are distinct, you'll never get a case where they're the same. So I guess I didn't have to think about that, but turns out I didn't need to think about that, right? So, okay, that's actually a nice realization. Since all the numbers are distinct, you will always guarantee to have all 4 indices the same, right? I mean, be different, right? Because again, if you have 0 and 3, you will not have like 0 and 4 because like, the number at index 0 doesn't change. And like, since all the numbers are distinct, it cannot be that the number at index 3 and 4 are the same. Therefore, that will not be possible, right? Essentially, what I'm trying to say is like, you'll always have, if you extended every single number inside of every single tuple in an array, you will only have unique elements, right? that's basically the point. Anyways, once you have these pairings, right, you know that you can map them together and they will form, valid tuples, right? And each one will form 8 valid tuples, as we said before, right? Essentially, you can think of these as A, B, C's, and D's, right? Where it's like, every single thing in here maps to the product of 12, so you can combine every single pair inside of these such arrays, and essentially be like, okay, augment result by 8 for every single pair, right? So then in an array like this, we have to ask ourselves, how many pairs are there in total, right? And if you do a little bit of mathematics, you'll realize that in every single array, the number of pairs will be n times n minus 1 over 2, where n is the number of elements in that array, right? For something like 1, it conveniently maps to 0, right? So if n is 1, 1 times 1 minus 1 is 1 times 0, which is 0. 0 divided by 2 is 0, right? So essentially, which makes sense, right? If you only have one pair and it maps with nothing else, then there's 0 tuples that you can make with it, right? For something like this, it'll be like, 2 times 2 minus 1 is 1. So 2 times 1 is 2, divided by 2 is equal to 1, right? So it'll be only like, one valid case. But, once we have found a valid A, B, C, and D pairing, we know that there's 8 valid tuples that it maps to, right? So in this case, it's like, only one valid pair, but for each pair, which for each pair of pairs, we know that there's 8 possible tuples you can create. So from this, we get 8, right? 1 times 8. And from this one, we'll get 0, 0. So the final answer will be 8, which is exactly what we get for example 1, right? So the point is, for each of these arrays, essentially grab the number of possible pairs of pairs, right? So each element inside of this array is a pair of indices, right? And now take these pairs of indices and see how many, pairs you can create between them, right? Which will be n times n minus 1 all over 2, where n is the length of an array, right? Now that you have the number of pairs, you know that each of those pair of pairs essentially form a valid A, B, C, and D permutation because they map to the same product. So we know for each one of them, again, there will be 8 valid tuples that come out of those pairs. So for every single product inside of our dictionary D, we're going to look at the length of the array and we're going to say, okay, the length of that array, what I want is I'm going to take number of pairs, which will be, okay, if n is the length of that array, it'll be n times n minus 1 over 2. And we're going to multiply that value by 8, right? Because it'll be 8 valid tuples from every single thing, right? In this case, it's like essentially for every single number of pairs, I added directly to res, and then I multiply res by 8 at the very end, just to make it a little bit faster. That way I only have to multiply by 8 once instead of every single time, right? So, but it's the same, right? Whether you do 8 times a plus b plus c plus d, right? This, 8 times a plus b plus c is the same thing as 8a plus ab plus 8c, right? It doesn't really matter whether you do it at the end, or every single time. It doesn't really matter. They're the same equivalent value, right? So that's essentially the point. Now, the only different thing I did is like, okay, for performance reasons, since I don't actually care about the contents of the arrays, I only care about the number of pairs. I don't really have to store the arrays themselves, right? I only need to store their lengths. So instead of appending a pair ij every single time, what I'm going to do is I'm going to essentially augment the frequency by 1 every single time, right? I'm essentially going to do plus or equal to 1. I'm going to get the value if it exists and augment 1. Otherwise, it's going to default to 0. 0 plus 1 will be 1 for the very first time that we see something, right? So that way we'll essentially have D map to frequencies, which essentially represent the lengths of those arrays, right? Using that length n, we can essentially calculate the number of pairs for every single value inside of our dictionary D, which used to represent our arrays, but now are just the length of the arrays. So for every single length, which we call product frequency, we'll do that value times that value minus 1 all over 2, which is the number of valid pairs, and we'll add that to our result, right? We really want to multiply that by 8, but instead of here, I'm just multiplying by 8 at the very end, right? And that's basically it. So for every single product, we see, okay, how many pairs of indices work for this? Essentially, you know, the values map to that. And it's like, okay, now that we have that, we know that every single pair inside of the list of pairs paired together form an A, B, and C, and D tuple that is valid. And for every single, you know, valid A, B, C, and D that we find, there are 8 possible tuples that correspond to it, right? So that's kind of the idea. We just grab the number of pairs for every single, you know, pair of indices that map to that product, which again, we keep through our dictionary D, and grab the number of pairs, multiply by 8, and then, you know, take the sum of all those results, and that's what we return. And it works very nice and efficiently. It gives us a beautiful, beautiful, beautiful runtime of 94.31%, which is exactly what we love to see. So hopefully that solution makes sense. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you next one. So until then, ciao, ciao, my friend. Bye-bye.